Welcome to Breadboarding. This is video 25 in the Breadboard 8088 PC series, and this is part 3 of looking at making our micro PC compatible, where we'll be building the BIOS and also looking at an issue to do with the timer and I/O wait states. Providing a BIOS compatible with the IBM PC software interrupts is the main thing in software we need to do to make a micro IBM PC compatible. But what is a BIOS? Well, BIOS stands for Basic Input Output System. The first BIOS was developed by Gary Kildell for Intel 8080 microprocessor around 1974-1975 and was used with CP/M, and this allowed CP/M to be used with different manufacturers' computers where the hardware specific changes could be put into the BIOS. It isolates the operating system from the hardware differences. It's known as firmware, so that's sort of halfway between hardware and software. In the early days this was built into ROM, latterly then into erasable ROM. More recently, modern computers tend to use flash memory. So the IBM PCXT BIOS supported 15 software interrupt functions. Wikipedia includes a list of these interrupt functions. So interrupt 10 is all to do with video services for doing screen updates and graphics. Interrupt 13 for low-level disk handling services. And keyboard was 16, and I think booting an operating system was interrupt 19 or 19. So PC BIOS source code was actually provided with the original PC, the PCXT and the PCAT technical references. So if you look at the PCXT that we've been working off, so probably about sort of 60, 70, 80 pages of BIOS source listing, and there are some sites where you can download this source code and build it using the Microsoft assembler MASM. We won't be using MASM, we're using NASM. It's a little bit simpler, but this is the code, for example, to do the sound beeps out to the timer. So clone PCs tended to use the BIOS provided by two of the main vendors were Phoenix and Award, and the setup screen, the blue setup screen that people may be familiar with, was introduced actually with these BIOSes. The original IBM PC, PCAT, didn't really have a BIOS setup screen. PCAT did have a configuration floppy disk, I think, that was used to set the time and things like that. Compaq developed a cleanroom BIOS for their Compaq Portable, and the way how they did this is that some engineers produced a specification from the original BIOS provided by IBM, and then the developer developing the BIOS never actually saw the IBM BIOS source code, so they could claim for it to be a completely cleanroom implementation. Now, the BIOS provides things like the power on self-test messages, RAM test and boot failure messages if it can't find a suitable operating system. So in the previous video we covered a number of these steps already, including testing the hardware output of the speaker circuit. What I'm now going to do is to show you what I did to download and configure Sergey Kiselev's 8088 BIOS, which is available on GitHub here. What we're going to be doing here is creating a breadboard PC configuration and configuration options. You'll see there's a number of different models of PC supported by the BIOS. Initially, for debug purposes, we're going to relocate the BIOS code rather than running at the top of the memory space up in ROM at F8000. We're going to move it down into RAM so we're able to debug it, and we can set software interrupts and various other things, and we can also use our built-in nanocomp monitor to help inspect memory and see what's going on. But we need to reduce the RAM for the BIOS to test to below this mark here, otherwise the BIOS, when it tests the RAM, will actually wipe out itself. I'm going to set the max RAM probably to about 256K to start with. We also need to make the changes to the monochrome display adapter configuration for the 6845 registers for our VGA output rather than the original MDA output. And we also need to add a little bit of extra configuration to configure the digital analog converter for the VGA output palette for the MDA controller. So those are slightly non-standard changes that have made to allow our MDA video controller card to be able to work with more modern video VGA compatible equipment. And then in order to run it, what we actually do is we set the extra segment in the nanocomp monitor using E to be 6000. So this is sort of in the middle of the RAM area, and that will mean that when we download the S record file, that will then go into the 6000 range, and then when we go to execute it, we set the code segment to be 6000 and then go FFF0, which is the standard reset vector on the Intel 8088 and 8086. So let's have a look at the BIOS code. So this is Sergey's site, and there's lots of good information on here, including how to build it and everything else. And what I would say is you need to make sure you install the necessary software to build this, and I'll just show you where that's configured in a minute. All I did just downloaded the zip version of this, and I've just expanded it into 2 folders. So I've got one folder here which is I've left as the master copy for comparison, and then I've got a BIOS breadboard PC version. And if we then look at these in WinMerge, so I'll ignore the binary files for the moment. So the main file which defines the whole BIOS is bios.asm, and there's a lot of documentation in here, so I'm not going to go through massive detail. One of the things to note is that a lot of the BIOS entry points are physically fixed, so that for software which doesn't call the software interrupt interface and actually calls some of these interrupt routines directly, then this ensures that compatibility with bad behaving applications is maintained. So you'll see quite often there are macros to space out the code to make sure that certain routines start at a given address, and that's the reason why there. You can see that the include files is where most of the information over these other files is actually just included into the main listing, and when we actually look at the output listing, you'll see that all of these include files will actually be in there. So if we just go through the changes that I've made, the default code segment for this is F000, which is the top of the ROM at the very top of the 1 megabyte address space. But for the purposes of loading this into RAM, I've disabled that, and we're putting this at 6000, which is 2/3 the way up the RAM. Due to the way how the configuration options were set for the breadboard PC, then when I disabled the real-time clock, then this int 70 was still enabled, so I needed to comment that out. So this just means that the code would compile. So that's a minor change needed to the base code. And then here I've got an extra include file for palette information. So this is the VGA palette register configuration definitions. Couldn't quite fit it in with the main video include file, and so this has just put it in a range where it would fit and not cause any problems with the mapping of the interrupt physical addresses. And there's a few minor things. So set lock is what is used to actually move individual routines to a defined fixed memory address. There are 1 or 2 cases where I just need to tweak these slightly, so this potentially could cause software that relied on those addresses to not work, but I think at the beginning of this, that's something that I'm prepared to accept. So that's all the changes I needed to make to the main BIOS. Probably the biggest change you need to make is in the configuration. So the configuration is quite clever. So all I've done here is, we can see that there are a number of different machines here. So we've got the Sergey's XI8088, and there's a number of other configurations here, including the original XT. And I've added a breadboard PC 8088. So whenever we see breadboard PC 8088, then that's the stuff I've added. So we've now got the options then for the breadboard PC. So we're starting the BIOS. Most of these are the same as the PC XT. However, whether or not we call it a PC XT or a PC 80, I'm not sure really matters very much. The configurations we've got here is similar to what the XI8088. So we've got the second programmable interrupt controller. I've added the mouse, and I've set the maximum RAM size, as I said, to 256. Although we have 512K fitted, we don't want the BIOS to test the upper memory where the BIOS is currently located. And there's a few other options and things in there that should be similar to what the original XI8088 was. So that's the configuration. Now the make file, make_win is the make file for Windows. And all I've done here is added in the extra ROM for the breadboard PC, and I've created a new target here for the breadboard PC ROM. What I have done for the moment is commented out the binary version, and I'm generating an S record form of the outputs. This means I can download it into the nanocomp cleanly. Then there's a few other changes. Messages, all I've done is added the breadboard PC for the startup screen in the BIOS when we actually get to see it. There was a minor change, this MISC one, again to change some of the physical entry points so that I could fit the changes for the video in here. And finally, the main changes I need to make was in the video initialization. So again, I've disabled the setting the locations here for this because it was causing too much trouble to try and get this to run. So what we've got here is, as part of the video card initialization, so if we've not got the breadboard PC, then this is the default settings for an original MDA video. That will be 720 pixels across and 350 lines down. Whereas if we've got the breadboard PC here, then this is the settings for the 80 by 25 mode, but with VGA compatible output. That's 640 across by 400 down. If we've got the breadboard PC, it will also call the init palette routine to load up the different color and black and white values in the video DAC. Now this is the init palette code, so this is very similar to the test code that we've got in the rest of the test functions. And if we just have a look at the palette, so the palette just includes the values for the different configurations. So whether we've got CGA compatible color, whether we've got the monochrome display adapter, black, green, dark green, bright green, or the white, light grey, dark grey. So if we have a look at the build instructions windows, I think it's in markdown format, so it's probably a bit easier to read it here. So what you need to do is to install NASM, which I'd already installed anyway, GNU make, and the core utilities, which included the TR package, and there's also the DD utilities also needed. I think this is used for merging the IDE disk BIOS. Then to build the BIOS, we need to make sure our path is set, and I'll test this one, and then we run make -f makefile.win. So that's as simple as it is. So if we go and have a look, I've got a command prompt here, and it's in the source directory. So all we're going to do here is just first of all check the various utilities are installed first. Do make, so we've got make installed, DD, TR, and NASM. So we've got all of the necessary utilities installed there. Then to build the BIOS, and that's built it. Then if we have a look at the srecord file, so you can see here that the srecord file is just going to be loading this. The srecord only does a 64K file here in our definition here. So when we're going to set the extra segment to be 6000, then that effectively means that this will be loading from 68000. We'll go all the way down to the bottom to 6FFFE0. This here is our reset vector, effectively. So in the previous video, I showed loading the BIOS and getting it running, and we were monitoring the power on self-test port, and we found that it got to about postcode 4 before it stopped. Now I was trying to do is to verify that the beep codes were working. In order to do that, I've updated the test program I was working on, and in addition to the power on self-test, I've now got the CPU error continuous beep at 400 Hz code copied in here. So we'd expect to hear a 400 Hz tone, similar to what we heard when we tested the speaker with the signal generator. So if we just download this to the Nanocomp, I'm just going to run it. In fact, all we can hear is a sort of not a very high frequency sound at all. And in fact, when we put the oscilloscope on there, it turns out that it's about 18 Hertz, 18.2 Hertz. So that was a little bit strange. I checked to see that the right values were being output, and it looked like the right outputs were being output to the timer chip. So this is the data bus. This is the programmable interval timer chip select. And what we can see here is we output B6, which is the control register set. Then we send out the A6 part of the timer, and then the 0B. So that's the least significant byte first, then the most significant byte. So we're definitely sending the right information out there. And after a bit of digging, I got to the bottom of what was going on. Now, 18 hertz is a little unusual because that's also what the system clock timer does, and what it does is actually set 0 to the countdown register, which actually does 65536. And if you work out what 1.19 megahertz is divided by 65536, it works out about 18.2. So what that indicated is that although we were theoretically sending the right configuration to the countdown timer, it wasn't setting it for some reason. So to cut a long story short, the issue is that I'm using the 8253 timer chip, whereas the XI8088 used the 5254. Now at the moment I don't have any of the wait states configured for the board because I haven't really needed them. For the RAM and the EPROM that I'm using is fast enough not to need that. Because the 8254 I couldn't really find a local supplier, I've got a couple of 8253s and they are almost the same. However, they aren't quite the same. And in fact, what I realised when I checked the data sheet is that the I/O write pulse time that we're currently using on the board is about 209 nanoseconds, and the 8253 needs 400 nanoseconds. So we've got the correct divisor and everything else, and if we just have a quick look at the logic analyzer output, but if we actually look at how wide this is, if you look at the top right hand side at the top here, the width is 200 and 210 nanoseconds here, which is just too narrow for this particular chip. So what we're going to need to do is to look at how to widen that. So have a quick look at the data sheets. So the 8253, the write pulse width minimum time is 400 nanoseconds. So that's about 2 clock cycles for the computer that we're using at the moment. You can see here, it needs to be a minimum of 400 nanoseconds. If we then look at the 8254, so this is a slightly more recent chip, and that has a minimum duration of 150 nanoseconds. So in fact, it looks like the problem we've got here is that the signal is appearing for too short a time for the 8253 to be able to update its counter. So we've sent the correct information out to the port, but because our pulse time is actually 210 nanoseconds, we need it to be 400. So what we need to do is add a wait state for I/O output. What I've done is I've opened the 8088 single board computer KiCad schematic, which is on Sergey's GitHub site. And all I've done is I've annotated a little bit just to try and understand a little bit better. Now the thing we really want is just this ready wait. So if wait goes high, then it basically just extends the current bus cycle, and as long as we can do that for an extra I/O phase, then that should actually be sufficient for what we need. So what we've got here is the I/O read and I/O write coming in to this flip-flop here, and it's also then hooked into the output. So the clear here is in fact coming from the ready wait. So this is quite a complicated circuit. So the output of ready wait goes into this flip-flop here and is then delayed by 1 clock cycle, and so the clear then comes back in here and clears it. So basically when we get an I/O read or I/O write, this will go high for 1 clock cycle, and then this will then actually result in clearing it within a cycle. So this is what we actually need. So combination of this one and this one is what we need. And whilst we're doing it, then down here is also the DMA request logic. What we're going to do is to add this as well. So this request DMA then comes out of here and is used to do the hold acknowledge, and the hold acknowledge again goes to the DMA controller, and then there's various other signals which are used for enabling and disabling the bus signals and things for when we're doing DMA. So I'm not going to go into great detail of this circuit because to be honest I don't fully understand all of it at this point in time. What I am going to do is to replace the gates that we've got here with the PLD, as I can do with this one as well. So what that should enable me to do is, once this has been wired in, then all of the reads and writes to the I/O devices should then be taking 400 nanoseconds. So in the next video, what I'm going to be doing is adding the I/O wait state logic and also the DMA logic as well that will be needed for that, and we'll carry on testing our BIOS. But really, until we've sorted out this wait state issue, there's no point in really looking at any of the other I/O chips because they may suffer the same problem. Then once we've done that, we'll be then building out the PS2 keyboard controller, the DMA controller. We'll then be able to add the floppy disk controller and hopefully then be able to boot MS-DOS from a floppy disk. So if you don't want to miss out on future videos, please hit subscribe, and if you could hit like as well, it just helps to make the videos accessible to a wider number of people. Thanks for watching.